Deep beneath the Pacific Ocean, about 1,000 miles west of Ecuador, there is a fracture in the seafloor that operates like a ticking clock. For at least 30 years, the Gofar fault has been operating on a relentless 5 to 6 year cycle. These analog seismograph recordings show a pattern that standard models can't explain. Every time that cycle resets, the fault produces a magnitude 6 earthquake that ruptures the exact same section of rock at the exact same size, over and over again. That kind of striking regularity violates the basic principles of earthquake science. We assume fault lines are inherently chaotic, building stress unpredictably until the ground tears apart in random destructive bursts. This perfectly repeating loop baffled geologists for decades. If tectonic stress builds at a constant rate, these ruptures should eventually escalate into much larger disasters. The fact that they don't means something physical down there is forcibly slamming on the brakes. To find those brakes, researchers launched a massive investigative effort, deploying ultra-sensitive seismometers directly onto the Gofar fault during 2 separate missions, 12 years apart. In the days and weeks leading up to a magnitude 6 rupture, the seafloor recordings show thousands of tiny micro-earthquakes clustering and surging within highly specific regions of the fault. But the moment the main earthquake hits, those exact same regions drop into near total silence. Because this identical sequence was observed a decade apart, scientists realized these sections are active barrier zones, localized stretches of the fault that repeatedly absorb stress without tearing themselves apart. The old assumption was that these barrier zones were simply dense, inactive blocks of solid stone that stood in the way of a moving rupture. Mapping the fault proved otherwise. In these zones, the rock splinters into multiple jagged strands, creating sideways gaps in the fault structure between 100 and 400 meters wide. This complex geometry interacts directly with the crushing weight of the Pacific Ocean. Miles beneath the surface, seawater seeps deep into these fractured zones, filling the porous rock and creating a reservoir of trapped, highly pressurized fluid. This combination of splintered rock and trapped water creates a volatile system that is uniquely sensitive to sudden changes in pressure. Geologists call the resulting process dialatency strengthening, and it is the physical mechanism responsible for stopping these quakes. When a large earthquake begins, the sudden movement forces the fluid-filled rock in the barrier zone to violently expand. As the rock opens up, the internal fluid pressure plummets instantly. Without that pressurized water providing lubrication, the jagged edges of the fault catch against each other and forcefully lock up. It functions like a car's anti-lock braking system. Instead of metal calipers, these porous, fluid-starved rocks act as built-in brake pads that clamp down on the fault. This instantaneous locking physically suffocates the spreading rupture. It ensures the earthquake stops dead in its tracks, preventing a magnitude 6 event from ever growing into something larger. While these findings came from the Gofar fault, this type of tectonic boundary exists throughout every ocean on Earth. For decades, geologists have struggled to explain why underwater earthquakes consistently remain smaller than geological models predict they should be. The discovery at Gofar suggests these break zones are a widespread feature of the global seafloor. This hidden network functions as a planetary defense system, actively restricting the reach of tectonic ruptures and preventing mega-quakes from reaching major coastal populations. After 30 years of mystery, ultra-detailed recordings have finally cracked the code of why these Pacific quakes are so strikingly predictable. While earthquakes on the surface are defined by chaos, miles beneath the ocean, the Earth operates within strict, orderly limits. Earth is a volatile machine, but understanding the hidden breaks built into its structure changes exactly how we forecast the boundaries of its worst disasters.